So yesterday we ended on page 3. Working this problem right here. And go back and forth. Okay. So this is where we ended yesterday, working this problem on page 3. We had just completed doing synthetic division, dividing this third degree polynomial by x minus 1, and the quotient was x squared minus 4x minus 1. So our fourth degree polynomial is now factored into x times x minus 1 times this quadratic. And so to find the last two zeros of our fourth degree polynomial, we have to set this quadratic equal to 0 and solve for x. Okay. So that's where we ended, right? We set x squared minus 4x minus 1 equal to 0, recognizing that a is equal to 1, b is equal to minus 4, and c is equal to minus 1 in this case. And then using the quadratic formula, we'll get the last two zeros of our fourth degree polynomial. Did anybody do that? Brian, what'd you get?
Yeah, 2 plus or minus square root of 5.
There you go. Okay. And so I got the same thing using quadratic formula. Okay, so you should be able to verify that. So the four zeros of our fourth degree polynomial are x equals 2 plus the square root of 5, 2 minus the square root of 5, x equals 0, and x equals 1 are the zeros for this problem. And now we can write out the complete factorization of f of x. And remember, the factors from these last two zeros, right? We got to subtract 2 plus the square root of 5 from x and 2 minus the square root of 5 from x. When we do that, we get x minus 2 minus the square root of 5 and x minus 2 plus the square root of 5. So that is the complete factorization for this problem. Okay? So 2 of the zeros are rational numbers and 2 are irrational numbers. Yes, sir.
So why didn't you check -1? That was the other 0.
No?
We plugged it in to the equation. It's off.
Right?
Yeah, we tried it. Yeah. Yeah.
Technically speaking, I didn't. Not during the lecture.
You only tried one more.
Yeah, you only did one, you didn't do negative.
Yeah. Minus 1 is not a 0. Okay. So we factored this and got, right? We factored out an x, so x equals 0 is a 0. And then when we, and then using rational zeros theorem, we discovered that x equals 1 is a 0. And so then we did the synthetic division to get the quadratic. And then solve for that, set it equals 0, and solve for x from that. So those are the 4 zeros, and this is the complete factorization. Any questions on that? Okay. All right. All right, last problem in this section. You'll have everything you need to successfully complete the web assignment homework. So we have f of x is equal to x cubed plus 2x squared plus 4x plus 8. Okay? And we gotta factor completely and find all the exact zeros of that polynomial. So, well, it's a third degree polynomial. So that's an odd number, an odd degree. So there should be at least one rational number that is a zero of that third degree polynomial. Well, it could be 3. It should be at least 1. Okay. So 8 is the constant term. And 1 is the leading coefficient. Okay? 8 is constant term, and the invisible 1 in front of the x cubed is the leading coefficient. So what are the integer factors of the constant term 8? Okay. Well, they're plus and minus 8, because 8 times 1 is 8. And they also include plus and minus 4, because 4 times 2 is 8. And so there's plus and minus 2 and plus and minus 1, right? So 8 times 1 is 8, and 4 times 2 is 8. So those are the integer factors of 8. Then we need the integer factors of the leading coefficient, 1, and that's just plus and minus 1. Right? The integer factors of 1 are plus and minus 1. Okay? So when you divide these 8 numbers here, up here, by plus 1 and minus 1, you just get these same 8 numbers over. Okay? So the possible rational zeros for this problem are plus and minus 8, plus and minus 4, plus and minus 2, and plus and minus 1. All right, so this make an observation about our polynomial. So there are 8. So there's a rational number that makes the right-hand side of our polynomial equal 0. Right? It's got to come from these 8 numbers. But we can narrow down the field a little bit, because all the coefficients in our polynomial function are positive. And so it's impossible to put a positive number in for x, and the right-hand side will equal 0. Okay? Because if you put in a positive number for x, you have a positive plus a positive plus a positive plus a positive, which is impossible to get 0. You got to have positive plus negative, positive plus negative, right? Negative's got to cancel the positive. So the value of x that makes the right-hand side equal 0 has to be a negative number. So now we can just consider the negative numbers in our possible rational 0. Okay. So all coefficients of f of x are positive. So we're just gonna look at the negative numbers in our possible rational zero set, okay? So I did -1, I put -1 in for x in f of x. And so you have -1 cubed plus 2 times -1 squared plus 4 times -1 plus 8. And when I did the arithmetic, I got plus 5. So minus x equals -1 doesn't work. X equals -1 is not a 0. So then I tried -2. So f of -2 is equal to -2 cubed plus 2 times -2 squared plus 4 times -2 plus 8. And when I did that arithmetic, lo and behold, I got 0. So x equals -2 is a 0 of our polynomial function. So that means x plus 2 is a factor of our polynomial. So the right-hand side, or polynomial function, can be written as x plus 2 times some unknown quadratic, right? First, degree 1 times degree 2 equals degree 3. So a quadratic goes in parentheses here. So by dividing the third degree polynomial by x plus 2, we can find the quadratic. And we can use synthetic division. So the 0, x equals -2 goes in the box. And then we write out the coefficients to the right, 1, 2, 4, and 8. Now you know the procedure for synthetic division. Bring down the 1. -2 times 1 is -2. 2 minus 2 is 0. -2 times 0 is 0. 4 plus 0 is 4. -2 times 4 is -8. And 8 minus 8 is 0. And you box the last number because that's the remainder. So we get a remainder of 0. Good news. So our quotient is x squared plus 4. There's no x term. So what goes in parentheses here is x squared plus 4. So now to get the last two zeros, we set x squared plus 4 equal to 0 and solve for x. So we can use the square root method in solving for x. Subtract 4 from both sides. Get x squared is equal to -4. And now you take the square root of both sides and you get x is equal to plus or minus square root of -4. And you know square root of -4 is not a real number. Square root of 4 is equal to 2. So the square root of -4 simplifies to 2i, right? Square root of -1 is I, square root of 4 is 2. So the last two zeros for our problem are x equals 2i and x equals -2i. And then we combine that with the rational number x equals minus 2. And we have all three zeros. Okay. Now I would remind you with what I was saying, homework, when I was looking at the problems, they don't ask you in those problems to list all the zeros. Not only ask you to list the rational zeros. Okay? So you would only write out the rational numbers. You would not write out the complex numbers. Okay? All right. So the complete factorization of f of x is equal to x plus 2 times x minus 2y times x plus 2y. This is a complete factorization. Okay? Any questions? Don't you just love math? I could do this all day. Okay? All right. So any questions? Yes, sir.
So you said there could be 3 possible zeros. So all we need is just one.
Well, you know what we said at the beginning, because this is an odd degree, okay, 1 or 3, there's either one rational number that's a 0 or 3 rational numbers are zeros, okay? And it turns out only one rational number is a 0. The other 2 are complex numbers. We didn't know whether it was going to be 1 or 3. We had to find them all before we knew whether it was 1 or 3. Okay? And why is it 1 or 3 and not 2? Because complex zeros come in pairs. Okay. So that's if there's if there's one complex number that's a 0 of this polynomial, then there's a second one. Okay. So that's why it was 1 or 3. Any other questions? Okay. All right, so we're going to move on to section 3.5. This is the last section from this chapter. Emma?
Just look at your question.
Rachel. so now we're gonna start talking about rational functions. And so, at the top of page 1, right, it gives you a definition of a rational function. And a rational function basically is got the following form. It's a quotient where you have a polynomial in the numerator and a polynomial in the denominator. Okay? So it's a quotient of two polynomials. There are no square roots or anything else, just two polynomials. So in the example 1, right, f of x is a polynomial function, right? The numerator is a polynomial of degree 1, denominator is a polynomial of degree 2. And then b, this is a polynomial of degree 3, and that's a polynomial of degree 2. Now, in working the examples A and B, you might want to draw a line, right, down the center of your page like I did to keep the two sides separate, okay? I'm just suggesting that, okay? All right. So in example 1, we got to find the domain and x and y intercepts of the rational functions. We've done that before with other functions, right? So the technique isn't any different from before. So in A, the rational function is f of x is equal to 3 minus x over x squared minus 4. Okay. So the domain, remember, there are no square roots, so you don't have to worry about taking the square root of a negative value. But remember, the domain is the set of all real numbers except for those numbers that make the denominator equal to 0. So one way of writing the domain is the denominator x squared minus 4 can equal 0, right? Because division by 0 is undefined. Well, using the square root method, right? You add 4 to both sides. You get x squared can equal 4. And then when you take the square root of both sides, you get x cannot equal plus or minus the square root of 4, which is equal to 2. So you get x cannot equal plus or minus 2. Okay. Now, if you prefer, you could have got the same result by factoring the left-hand side. Okay. If we had started with x squared minus 4 can equal 0, you know the left side's a difference of squares, and that factors into x plus 2 times x minus 2. And now you set each factor not equal to 0. You get x plus 2 can equal 0, and x minus 2 can equal 0. And you end up with x can equal negative 2, and x can equal plus 2. Right? Same as over here. I made a mistake. That should not be square root of 2. Square root of 4 is 2. So you have x can equal plus or minus 2. You get the same thing over there. Okay? So whatever approach works for you. So the domain is all real numbers except for minus 2 and plus 2. So how do we do that interval notation? Parentheses, minus infinity to minus 2, union, parentheses, minus 2 to plus 2, parentheses, union, parentheses, 2, plus infinity. Does that look vaguely familiar from previous exams, right? Math is cumulative, right? So that's the domain in interval notation, okay? Now to find the y-intercept, what's the procedure? Set x equal to 0 and solve for y. So the y-intercept is just the value of the function at x equals 0, right? Set x equal to 0 and solve for y. Remember, y values and function values are the same. So when we put in 0 in for x on the right-hand side, we have 3 minus 0 over 0 squared minus 4, which is just equal to minus 3/4. So minus 3/4, or the point 0 minus 3/4, is the y-intercept for this problem. Any questions on that? Now to find the x-intercepts for this rational function, we set y, right, y in place of f of x, equal to 0, and then solve for x, right? So you just set the right-hand side of the function, 3 minus x over x squared minus 4 equal to 0, and then solve for x. Now, there are no common factors in the numerator and denominator. What we're going to learn is that when this is reduced, there are no common factors in the numerator and denominator. To find the x-intercepts, all you got to do is set the numerator equal to 0 and solve for x. But we'll explain, see why, right? So in solving for x, right, multiplication undoes division. So we can multiply both sides by x squared minus 4. And so on the left-hand side, x squared minus factor x squared minus 4 cancels, and you're left with 3 minus x. But on the right-hand side, you get 0 times x squared minus 4, which is 0. And so that's why you just didn't find the x-intercepts. If there are no common factors in the numerator and denominator, all you got to do is just set the numerator equal to 0 and then solve for x. And so we end up with x equals 3, or the ordered pair 3, 0 as the x-intercept. Everybody follow me? All right, so let's look at B. This one's a bit more challenging. We have f of x is equal to the third degree polynomial x cubed plus 2x squared minus x minus 2 over x squared minus x minus 6. Okay. So the domain for this rational function, the denominator can't equal 0. Well, that factors with whole numbers. It factors into x minus 3 times x plus 2 So, x minus 3 can equal 0, and x plus 2 can equal 0. Solving for x means x can equal 3, and x can equal negative 2. So what's the domain in interval notation? Parentheses minus infinity to minus 2, union, parentheses minus 2 to 3, parentheses, union, parentheses 3 to plus infinity. That was so hard to do at the beginning of the semester, right? Now it should be getting easier. The y-intercept for this problem is equal to f of 0. Well, when I put in 0 in for x, the right-hand side of our function, right? 0 cubed plus 2 times 0 squared minus 0 is all 0, and I'm just, right, you're just left with a constant term in the numerator and the constant term in the denominator. You get minus 2 over minus 6. Simplifies to 1/3. So y equals 1/3, or the ordered pair 0, 1/3 is the y-intercept for this problem. Now finding the x-intercepts is a bit more challenging, because you got to set the right-hand side here equal to 0 and solve for x. So you're going to have to check my math, check my work. But the numerator, using the, right, this is a third-degree polynomial, so at least one of the zeros has to be a rational number, okay? Or one of the factors, right, has a rational number. So using the rational zeros test, and I also observed that by putting 1 for x, the numerator equals 0. The numerator factors into x minus 1 times x squared plus 3x plus 2. And we know the denominator factors into x minus 3 times x plus 2. So I got this using the rational zeros test, which we just, previous section. And then this quadratic in parentheses, right, it in turn factors into x plus 1 times x plus 2. Okay. So minus, you know, see this is a common factor. You can't just set the numerator equal to 0 and solve for x, because x plus 2 is a common factor in the numerator and denominator. And I just erased the domain, but x equals minus 2 is not in the domain. Okay. So to find the x-intercept, first you got to cancel out the common factors. Okay. And what's happening at x equals minus 2 is there's a hole in the graph. When you have the common factor in the numerator and denominator, that means there's a hole in the graph at that value of x, at x equals minus 2. Okay. So In reduced form, our function is equal to x minus 1 times x plus 1 over x minus 3. This is called reduced form. So I'm finding the x-intercepts. X equals minus 2 is not in the domain, but what's happening at the graph at x equals minus 2 is that there's a hole in the graph. At x equals minus 2. Okay. So now we can set the numerator equal to 0 and solve for x, and that'll give us the 2 x-intercepts in the graph of that rational function. So we have x minus 1 times x plus 1 is equal to 0. So x minus 1 is equal to 0. X plus 1 is equal to 0. Which means x equals 1, or the ordered pair 1, 0 is the first x-intercept. Then we solve the second equation for x, we get x equals minus 1. So x equals minus 1, or the ordered pair minus 1, 0 is the second x-intercept. Okay. So there are not 3 x-intercepts, even though there are 3 factors in the numerator here. There are only 2, and there's a hole in the graph. Okay. All right. Any questions on that? All right, so if you flip over your page, you know what? I don't want to start example 2 and then stop in the middle of it. So let's get a jump on the weekend, okay? And we'll pick it up here on Monday. But remember, homework 3.4 has been released and it's due Monday night, okay? So I'll see you Monday. Have a good weekend.